Welcome to the first Friday seminar of this academic year. And today we have a pleasure to have Aidan Herderschee, who is a new member, and he will tell us about the next leading order, scattering waveform from scattering amplitudes.
Thank you for having me. Very happy to be here and share some exciting work that I've been doing together with collaborators, Radu Roybin and Fei Tang at State. Before I get into it, some papers that if you just want to look at if this actually strikes your interest, or you just don't understand what I'm saying and just want to go to the paper, like I sometimes do. The paper that I'll be mostly following is this one. I will note that there was an oversight pointed out by a paper by Sebastian, Hoffy, and Simone. So there's an upcoming correction to this paper this week. So not everything in there is totally correct, but everything in this talk is, and we just are trying to dot all the I's. A similar calculation was done by Queen Mary at the same time. There's a group at Queen Mary. And then also there's a paper by Don O'Connell et al. And some other people that also came out at the same time doing a similar calculation except in E&M instead of gravity. And then finally, there's an upcoming paper by Demore that is unpublished that does the same calculation in a different expansion using a completely actual GR calculation. So there are lots of people doing this kind of thing, and you should just look at the paper that you understand the most if this talk is interesting to you. So the motivation, before you do physics, you should understand why you're doing physics. So what am I actually computing? What I'm computing is that the observable I'm going to compute is that you have two black holes come in. They classically scatter off each other. They emit some radiation during the scattering process, and I measure that radiation at a detector on Earth, or just anywhere. Note that you've heard probably a lot about waveforms from LIGO. This is not the kind of waveform that LIGO is measuring. So LIGO is measuring bound waveforms. So they're black holes that are coalescing. And the waveform looks like this, where it gets higher and higher frequency, and then it peaks, there's a merger, and then there's a ring down. This has a very distinct signature. The calculation that I'm describing here is not this. It looks more like that. It's just like a blip. It's not a continuous sequence. So it's not something that we're actually measuring right now, or I don't think is measurable in the foreseeable future. But I can also argue that it's an interesting observable to look at for basically two classes of reasons. The first class, I should just write down scattering. The first reason is that LIGO needs, in general, better waveforms for the next generation of detectors. So the next generation of detectors, currently we measure frequencies of about 1 hectohertz. The next detectors the ground-based ones are going to be about 1 hertz, and then the space-based ones will be about 1 millihertz. Currently, I think the waveforms, improving the waveform does not help that much because there are larger systematics. But as you get to ground-based and then space-based waveforms, I think I have been told, even though I haven't cross-checked it myself, that they basically want 1, maybe 2 orders of magnitude improvement in the accuracy of the waveform to actually do very precise measurements. How does that relate to an observable that's not actually the bound waveform? Well, the idea here is that a lot of the techniques that you can use to compute the bound waveform can often be imported into the scattering waveform. This is most obvious in the conservative sector, where there's a paper by Rafael Porto et al. That showed how you could actually do a direct analytic continuation. So you could take the result that you computed for scattering, and you would just take that function and do an analytic continuation. And after you did the analytic continuation, you would get the result for the bound waveform. So in that specific case, literally doing this calculation was the same as doing the bound calculation for a subclass of observables. This is not generically true, but it's not as easy as doing an analytic continuation. But there is just this general idea that by doing calculations in the scattering regime, a lot of these techniques, such as integration by parts, unitarity, all that jazz, can be then imported into the bound waveform, people who are doing bound waveform. And we've actually seen some results there. People there are now actually using FIRE and integration by parts for these techniques that they weren't previously doing. So maybe you can argue how much I overstate the usefulness. I think that's a matter of taste, but there is just a statement that there has been a connection between these two communities, and computing the scattering has been helping with computing the bound. That's the practical motivation. Now we go to the formal motivation, which is the stuff that I actually care more about, which is Which is that the waveform is an interesting observable to study for a multitude of reasons. First one, it's actually not an amplitude. This was really emphasized in the Sebastian Hoppe paper. This is like an out-of-time correlator. So even though it's an asymptotic observable and you can compute it using amplitude techniques, it is fundamentally not an amplitude. And this is very useful and very interesting because you can actually, as I'll get to later in the talk, you can show that the amplitude doesn't have a valid like semi-classical limit, but the out-of-time correlator. And this is pretty interesting that you can take an object which doesn't have a valid semi-classical limit and you can use those techniques to actually compute something that does. So here, like first reason is that it's just not an amplitude and it's interesting to compute new observables. The second reason that I was mentioning before is classical physics. I think something that's still not super well understood or not completely understood is how classical physics emerges from quantum physics. Here, what I'm going to show you very directly is how we can actually take techniques that were used to compute quantum amplitudes, and you're going to use them to compute a classical observable. And you're going to like see the emergence of classical physics from quantum objects. And I think that's like amplitudes are an intrinsically quantum object. How am I possibly computing something that's classical from it? I think that's a fundamentally like interesting question.
We usually say that three-level amplitudes are equivalent to solving the classical complex solutions of the classical equations.
Sorry, do you mean in like the world line formalism? Or
in any formalism, so normally the statement is that three-level amplitudes are the same solving the classical equations.
I think this depends on your definition of classical. The definition of classical, I will use, okay, so this, I should have been more careful with the definition of classical. The definition of classical I'm using is working in the large quantum number regime. And I'm going to show that the amplitude in this, like the quantum numbers that I choose in that large quantum number regime, the amplitude does not exist. That is the sense in which I mean classical, that I'm going to be working at asymptotically large quantum numbers. If you just equate classical to tree level, then yes, like tree level amplitudes are classical. The third reason, which this will be, I think, a mixed bag for who actually believes this or not. Amplitudes are interesting, I would argue, to study by themselves. They have interesting structures, they give you interesting functions. However, amplitudes are too complicated to study in complete generality. So usually you look for specific simplifications, like n equals 4 super Yang-Mills, n equals 8 supergravity. You look for regimes where the calculations are computationally tractable and you can actually make progress. And then you see like how much of that structure generalizes into the more complicated case. It turns out going to the classical limit for scattering amplitudes, or what I will define as a semi-classical limit, leads to dramatic simplifications in the integrals. For example, in the classical limit, people are actually seriously doing 4 loop integrals that have physical relevance. And I don't really think like the highest I see is 3 loops usually, or like two or three loops at like collider Fido stuff. But they're actually going to 4 loops, and they're doing like a real 4 loop calculation that has physical relevance and could actually potentially be useful at some point in the future. So like here, I think it's just simplifications. If you look at integrals and find amplitudes in particular limits and you see simplifications, then there might be some generalization to not the classical limit. Okay, so that's the motivation. I hope I've convinced you this is not a waste of time to study, and that at least it has like relevance for LIGO with my wiggly lines, and there's also like a formal relevance that these things are interesting independent of experiment. Okay, so now I'm actually going to go to first, what do I define as the classical limit, following off Juan's question. So the kinematic process we were considering, as I said before, was like 2 black holes coming in, scattering off each other, and then having a graviton go away. But you actually have to define a perturbation parameter. And so what is our perturbation parameter going to be? What are we going to take to be large? What I take to be large and what people call this the post-Minkowski expansion is that you take the impact parameter to be large. So if I take 2 black holes and they scatter off each other, I shouldn't show them intersecting, but like their impact parameter, like the distance between the black holes is what I take to be asymptotically large. And then you can use this to say, how does this connect to the amplitude? So the impact parameter, I say the impact parameter scales as 1 over h bar. impact parameter is conjugate to the transferred momentum. So this implies that I'm going to be basically looking at a 4-point amplitude with two massive scalars, and I am going to be saying that the transferred momentum, which I denote as Q, scales as h bar. In addition to that, I will also be saying that any external graviton radiation will also scale as h bar. Basically, that the emitted energy of the graviton is asymptotically smaller than the mass of the actual black holes that are coalescing. And here I can actually, I'll draw the diagram. This is the graviton that's being emitted, and then these are the two large scalars that are coming in and going out. And these I'm taking their mass to be basically asymptotically large. You can show, just because there are like a finite number of scales in the problem, that the limit that I have taken here is actually equivalent to saying that the masses of the black holes are just asymptotically large. And you can actually match this in this limit to heavy quark effective theory. So you can take that the limit, you can show that the limit I am studying is equivalent to the heavy quark effective theory limit, except like the black, I'm going to say that my black holes are just scalar particles. Now we get into what I mean by when I said the.
Why do you need the loop in the middle now?
Oh, sorry, it's not. I just meant like a blob. Sorry, I can say like the tree level process is just this. Sorry, that wasn't meant to be a loop, even though I can understand why that might have been. I could have maybe filled it in. Now we get into why I'm going to make the statement that the amplitude does not have a valid semi-classical limit. You already see an artifact of this at tree level. So at tree level, let's consider the process. Just two black holes, like one black hole comes in with some radiation. The scattering process happens, and then the black hole goes out with some radiation. And I'm now, like the impact parameter thing doesn't actually matter, but I still take the limit that my external momentum, the external momentum of the gravitons are asymptotically soft. If you just take the tree level amplitude and do the expansion that the asymptotic momentum is that the outgoing graviton momentum is asymptotically soft, you find that the amplitude takes the form I'm not going to have enough space for this. I'm going to go over here. There might be a 2 pi factor there, but I assume nobody cares. That's not actually relevant. Again, there are some factors that I'm 100% forgetting about, so let's just ignore the factors. The key point here is that if you take the h bar scaling of this amplitude, you will show that this part has the h naught. This is the classical part of the amplitude. However, you can see already at tree level that there is this term, where if you calculate the scaling that I described before, you get a 1 over h bar from this delta function, because you take the k to go to k goes to kh bar, and this leads to a 1 over h bar here in this term. This is called a superclassical term. This term is basically the reason why the amplitude doesn't have a valid semi-classical limit, because while this term already you should signal to you it's kind of weird because it only has delta function support. what happens is that as you go to higher loops, there are other superclassical terms as well that also like now, because there is an integral, they actually have full momentum support. But as you show that it's as you go to higher and higher loop order, you generate terms that are higher and higher order in 1 over h bar. That roughly it goes as 1 over h bar L plus 1, something like that. So as you go to, if you include higher and higher loops and you try to take an h bar goes to 0 limit, you actually have to like the highest loop contribution that you calculate is actually the thing that dominates in the 1 over h bar limit. But these contributions are trivial in a sense. These contributions are basically like, this is the delta function, like the way you should interpret this term is basically a classical event happens, like this is just the 3-point classical 3-point amplitude. There's just matter propagation over some like arbitrary amount of time. And then the second event happens and then it continues on going. And all super classical events are like this. They're just the products of basically super classical events are just the product of classical events that happen. And then you can show that, again, this is why the amplitude does not have a valid semi-classical limit in the expansion that I'm defining. Yes, no, it can be resummed. In the I was going to get to this later, but you can show there is an argument that the amplitude in the semi-classical limit resums. I'll just say it now. That there is a WKB approximation, basically. So this is the sense in which you can show that n, or there's not a proof, but there's like an argument that n has a valid semi-classical limit, S does not, and the superclassical terms come from iterations of this n hat operator. I'm going to erase that for now. Okay, that's the classical limit. Does anyone have questions on that? Does everyone knows classical physics now? Okay. We're now going to get to the second part, which is out of time correlators in KMOC. And I have a discussion. I'm going to do a mix basically of the discussion in my paper and the discussion in Sebastian Hoppe et al.'s paper as well, since I really like how they phrase it.
Sorry, I have a question. After the superclassical terms, are you saying that if you have all the entire resummed amplitude, it's no longer analytic in h bar? Like it's something like e to the 1 over h bar. And
like this, the thing that I erased, the n goes as like roughly 1 over h bar, basically. It's the same thing that when you do a w, like when I write an exponential, like exponential 1 over x, where I take x to be small, that doesn't have a valid Taylor series expansion. You need to do a trans series. That is the sense in which I am saying that this doesn't have a semi-classical limit. The amplitude doesn't have a valid Taylor series in h bar. Only the exponential does. You should think of it as like an operator trans series. Okay, now we get to KMOC. So when we're actually computing these correlators, the amplitude doesn't have a valid semi-classical limit. So the question is, what should we actually be computing? So what these people from a KMOC paper that I've not written the number down and don't remember it off the top of my head, is they tell you is that the way that you should compute an observable is that you just take your end state, you evolve it using the scattering matrix from negative t infinity to infinity. This gives you your out state, and you just measure your observable in the out state, and then you subtract what you would have measured from the in state. Note, this is not a scattering amplitude. You can relate it to scattering amplitudes as I'm going to do, but this is specific. This is intrinsically not a scattering amplitude because S is appearing twice. Because if I substitute in this formula here, you can see that S is appearing twice. It's not just a scattering amplitude where S only appears once. In addition, now what you can do is you can say, well, like we don't usually actually do computations with S. We do computations with the transfer matrix. So scattering amplitudes are computed by basically saying I'm ignoring the trivial events that could occur and I'm only including the complicated connected events. And you can just take this formula and you substitute it into KMOC. And you get this very nice looking expression, which was the core of the KMOC paper. So how should you interpret this? What O is eventually going to become when I'm computing the waveform, O is going to become a creation and annihilation operators for the graviton. So these two things are just going to become like the 5-point amplitude and its conjugate. And those are just scattering amplitudes. Like I can compute them using scattering amplitudes techniques that have been known since the 1960s, even though this only really became practical probably in the last 10 years. This last term is hard, or not hard, it's like the new bit. This is the non-trivial bit that basically corresponds to the fact that you're actually not computing an amplitude. The way you should interpret it is as a cut. So the way that I compute this is I say, well, okay, these are operators multiplying each other. I need to like insert the identity operator. What is the identity operator? It is the taking like a sum over all possible intermediate states. So I insert this identity operator here. And now you get amplitudes. Like this evaluates to an amplitude, this evaluates to the amplitude, and you need to do a phase space integral over all intermediate states. This is not a cut, but it is, you can compute it in the same way that you would a cut effectively. Because the operator insertion is between the two things, it's not, you can't relate T times T dagger to T minus T dagger, but you can still use the same computations the same strategies for computing a cut that you would to compute this term. Okay, so then now everything I've told you with KMOC is valid. So I should write this is 2. This is all valid for a generic quantum amplitude. At tree level, this like nothing really happens because this cut term doesn't contribute at tree level. So at tree level, like there's really no difference between just computing an amplitude and computing this out of time correlator. But at one loop, if you just want to do a full like quantum computation, you could go and just compute T fully, like not taking any semi-classical limit and just say, this is what the out of time correlator is in my system. However, the other key insight in the KMOC paper is that this formula simplifies a lot in the classical limit. And that's what I'm going to describe now. So here we should ask, like, when am I taking my end state to be? I'm taking my end state to be black holes. Okay, I'm good on that. So I'm computing my end state. It is in, you can see I'm Fourier transforming to impact parameter space. I'm not Fourier I'm Fourier transforming to position space, and I have some wave functions here in momentum space.
Sorry, just a quick, have you already used the fact that you're working at large quantum numbers?
No, not yet. So
That assumption is only saying that you
Yeah.
have to solve it.
I have, yes, in this section 2, like the KMOC thing, I've not yet used anything about the classical limit. The formulas that I've written down are completely generic.
The fact that the series is not well defined has nothing to do with these like sort of
Well,
other series in 1 over h bar. Like this classical limit is not related with these large quantum numbers.
sorry, the statement that I'm going to show is that when you're computing an observable with KMOC, it does have a valid classical limit. That is the statement I'm going to make. So even though the amplitude doesn't have a valid classical limit, these out of time correlators do. And that's I think really one of the non-trivial insights of this KMOC paper, is that you can do like this classical limit doesn't apply to amplitudes, but if you're actually computing observables or that n hat operator I wrote before in the exponentiation, you can show that those operators actually do have like, they are like, you can do a series expansion H bar and just truncate everything except the leading order H bar term. And I'm gonna, like, this is the section where I can argue, like, show, at least partially argue that. The proof is somewhat technical, and I'll leave that to experts, but I can argue roughly how it happens. So here, we take this in operator, where you're doing this phase space like integral. And note that I have an in operator over here, and I have an in operator over here. So there are two in operators. And then you can show, I'm going to ignore P2 since the same thing happens for P2. So here, now this is where the magic happens, so to speak. I'm doing an integral over both the incoming, like the momentum of my large black hole on one side and the integral of momentum on the black hole on the other side. However, remember I'm taking the transferred momentum to be small. So here, I'll write it over here. I am taking the difference between P1 bar and P1 to be small. I am taking it to be order H bar. So you can say that this is actually P1 plus Q. And this just becomes Q times B1. And if you assume that the things in the dots, which I have not proven yet, but just take my word for it, has a valid semi-classical limit and you're only taking the leading order piece, you can just say that the leading order contribution H bar to this is just, you discard this, and then you do a change of variables from dP1 bar to Q. And you can see now that I've actually reproduced like this impact parameter like limit comes very naturally from the KMOC formula. Again, this is only works if you're working in the leading, like this algebra here, I am assuming that this term dot, 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 I am taking the leading order contribution in H bar. If I was not taking the leading order contribution in H bar, the series expansion of this wave function would like non-trivially interact with it. But I'm implicitly assuming that whatever is in the dots can be series expansion H bar, and I'm only including the leading order term. And if I do so, I get this nice formula where I can relate this KMOC and impact, where I'm doing this KMOC formula for the scattering amplitudes to just doing a Fourier transform to impact parameter space. And then I just ignore this. I assume that my wave functions are like delta function supported or like near delta function supported. Yeah. So now we're almost done with I'm almost done with KMOC. I'm going to give a bit of a physical picture now for what the difference between KMOC and a scattering amplitude is. So in words, the difference between KMOC and a scattering amplitude is the statement that a scattering amplitude is an exclusive observable. When you're computing a scattering amplitude, you are saying there's an input state X, there is an output state Y. What is the probability that I get Y and nothing else? What you're doing with KMOC is that you're basically saying, I am measuring this one specific observable, and I don't care about the rest of the state. So here, if I draw it, this is a nice picture in Sebastian and Hoppy's paper, which I'm just stealing. And here's the external states that correspond to my operator. Oh, but let's say there's also like emitting a bunch of gravitons over here that don't affect the observable that I'm measuring here, because the waveform corresponds to just one graviton, but let's say there's like a bunch of, like I'm going to higher loop or something, and there are a bunch of gravitons being emitted in the final state. When you're computing KMOC, you're integrating over all these states. You're saying I am including all states that have just at least one graviton. I am not excluding to only one that has that graviton and nothing else. And it turns out that that magically allows you to actually take a set, like a classical limit. Basically, that is magic and what is the difference between an amplitude and just this actual out of time correlator. Is the statement that instead of just picking one event and saying, I'm only measuring that and nothing else, you actually say, I'm going to say, I'm including all possible events I could measure, and then I'm taking an average over the expectation of my operator from them.
What's KMOC stand for?
It's the name of the people. I know O'Connell.
Okay, fine.
I think David Cowan, yeah.
Another question is, this type of observable is common when people discuss expectation values of operators in interacting systems. It's normally computed using a two-sided contour.
Yes, yeah.
It's completely equivalent discussion.
Yes, yeah. There's a nice discussion of this in Sebastian's paper. You can in principle use this technique. And I think like computing the susceptibility of like condensed matter systems to long wavelength radiation.
Right. So in that formalism, there are two copies of the space-time, the propagators.
Yes, yeah. This corresponds to the fact that I have an S and S dagger here. Like S evolves my system forward, and then I have an S dagger that evolves my system back.
Another question is the discussion you said in the blackboard on the top right, is that somehow equivalent to saying you have a heavy sort of gravitational Wilson line?
No, not quite, because this is allowing for corrections to the path. So if I only had a Wilson line, I would be saying that my path is not corrected. But this allows for the fact that there can be like back reaction that actually changes the path of the particle, albeit like in a small way.
I thought that would be like a small change in P, but you did not include the small change in P.
Well, I had to be very careful, like
That's why I was.
Sorry, the fact that I'm allowing the Q transferred momentum is basically what allows the path to deviate. One way you can phrase what I'm doing is that I'm calculation deviations of the path in 1/b. So leading order, the path is just a line. But if I'm trying to systematically include corrections in 1/b. And basically the way, like you have to be very careful to make sure that the H bars all cancel and everything. But what it ends up being is like 1/b corrections to the path. The reason it's not quite, again, I want to emphasize that the classical limit, taking the H bar limit is very subtle, because you can actually find that there are like H bar over H bar calculations in intermediate steps. So that's where it basically comes from, that it's not just a Wilson line. Oh, wait, sorry, did that answer your question?
Okay, yeah.
Okay.
Yeah, I was wondering, in what sense is this an out of time order correlator? I think usually, or the ones I'm familiar with, you go back and forth and back and forth. But what's out of order here?
Yeah, it's the fact that you have an S and S dagger here. Like the S evaluates your system forward in time, and then the S dagger evaluates your system backwards in time.
Okay, so it's not the same kind of out of time order.
Oh, it's not an amplitude like this. Sorry, you could use this.
I think Jonah is just it's a language issue. So
Yeah, I was wondering if there was a connection to the
Yeah, it's
other.
normally not called an out of time order correlation.
Oh, okay, fine.
Because it's an expectation value, something you could compute in a physical situation.
Right.
Normally, things that are called out of time order correlators, something that you need to do something physically funny, like evolve the system backwards in time and so on.
Okay, I guess that is okay.
Here, it's automatically done because you have the brand again.
Yes,
In a physical situation.
I guess the reason.
Yeah, it's a normal. It's a normal expectation.
Well, okay, but you are evolving your system back in time with that stagger. Like you're.
That's in the formalism.
Okay, fine, okay, yeah.
It's a language issue.
Okay,
Okay, so no connection to the other, like the chaos stuff.
well,
Okay,
I'm not
maybe
gonna-
I'm opening the box.
yeah, I'm gonna keep that box closed. That's,
If you're a sophomore, you would call it an expectation value.
fine, whatever. Okay, fine. I think the most accurate way you can call it, like the most language respecting thing you can do, and maybe don't. No, it's not expectation, it's an inclusive observable. You're summing over all possible, there's a difference between an expectation value where you just have a definite state, and then here you're,
Sorry, then is out not a definite state?
sorry, out is a definite state, but it's like a coherent state of gravitons, for example. Like
So,
there are a bunch of gravitons at infinity that you're ignoring.
But it is just an expectation.
Yes,
value
okay,
of
yes,
the
from that
amount.
perspective, yes, okay. You're just taking an expectation value out.
Your emphasis is not an amplitude. So for people who are not computing amplitudes all the time, the expectation value is the perfect.
Yeah, fine.
Okay, yeah, sorry.
Okay. It is just an expectation value, but you do have the S that's evolving things forward and backwards for the record.
It's the language.
Wait, were there any more questions? Okay, I'm going to keep going. Okay, so right now I've described KMOC. I've described how in the leading order H bar limit, there's a simplification with KMOC. The argument that I'm just going to say, I'm just going to sketch it quickly, is the statement that if you actually wanted to show that the thing that's entering in this ... actually does have a valid semi-classical limit, what basically the proof strategy that you should use is you should write S equals I n hat. Assume that n hat has a valid semi-classical limit, and then plug that into the KMOC formula, to the original one. You can then basically show that all the semi-classical terms cancel out. Like there are products of n's, but they come with additional H bars. So they don't generate super classical things. You don't get the product of n's that is the super classical terms in the amplitude, but that's something for the experts. Okay, now I'm going to go to section 3, which is the very technical section, which is actually how you do this computation. Actually, I'm going to erase this stuff. Okay, so now we need to say, I've given you a general formula for how to compute things, but what is the actual thing that we are going to compute? People have been using this formula for things like the impulse. So for example, you can measure the change in momentum during the scattering process using this formula. The thing that we're computing is the waveform. So we're computing the linearized Riemann tensor. And so what you do to compute this is you just go into Sean Carroll or whatever your favorite GR book, you look for the equation for the linearized tensor, you assume that your graviton at affinity is weakly coupled, so you can do standard quantization, and you take that formula for the graviton field and you just plug it into the Riemann tensor, like the formula for the linearized Riemann tensor. And then you ultimately get I'm gonna just not even attempt to keep track of factors. So if you go and do the procedure that I've described, this would be something in like a first year QFT class, you can get this nice quantized formula for the Riemann tensor at infinity. Here I've used again the assumption that it's weakly interacting. Like I am working at like large spatial distance. So I can actually just plug in the original formula without any interactions. So then I just take this formula for the Riemann tensor and I set this equal to O and I plug this into my KMOC formula over there. I have the creation operator for the graviton, and then it's a complex conjugate, and I get the annihilation operator. And those, like these things I can roughly pull out, and the O's like just roughly become computing things like A, T, or T dagger A, or like cuts of this form. The one simplification that we also make in the paper is that this is still a kind of annoying formula to do, because you need to do this integral over the face, over the phase space of the external graviton. So now you have to do 2 additional integrals in addition to actually computing your amplitudes. You need to compute this impact parameter integral, and you need to compute this phase space over K. However, we are working again at large spatial distance, so you can use a saddle approximation. Because you have this delta function over here for K squared, this is actually, you can write this in a way that's not linear. This is not just a linear Gaussian, it's actually quadratic. And you can take the large spatial distance to do a saddle approximation. Again, that doesn't have anything to do with the classical limit. It's just the statement that we are working at large spatial distance, so you can just use saddle. That's like, it's just the standard Gaussian integral. It's like a little bit of algebra, but not very complicated. You ultimately get 4 saddles. You can show that 2 of them vanish because they are advanced, and then because basically they have advanced time, and you can show that they just go to 0 from a careful analysis. And then 2 of them have like are a function of retarded time. So roughly you can just make the replacement. I'll just write the t here, defined in the t. You can just make the replacement that if you have this integral here over k, you can replace it with just this 1D integral over omega. And then this is the thing I actually won't go into detail because it's just really annoying. You can combine this omega integral with the impact parameter integral to actually like simplify that. You can show that if you combine the omega integral with the impact parameter integral, for certain parts of the computation, you actually just get a delta function. So instead of, you've converted this like double integral over q and k to just a delta function integral that you just like delta functions are trivial to evaluate. This doesn't happen for all the terms, but there is like in general a dramatic simplification when you actually treat this integral over omega and this integral over q simultaneously instead of trying to do them separately. Okay. So now I actually go to the last step of this computation, which is doing integrals, which I know everyone loves from their first QFT class. These integrals it's going to correspond to a 5-point.
An example of the Feynman diagrams very well.
Yeah, I'm about to write it down. Yeah, sorry, yeah. Yeah, so at tree level, the Feynman diagrams are kind of just this, and then you take the H bar limit. At one loop, it becomes more complicated. We don't actually compute it using Feynman diagrams. We use something called generalized unitarity. So generalized unitarity is the statement that if I give you an integrand, I can reconstruct it from its cuts. So I can set certain like propagators in the integrand to be on shell, and then it just factorizes into product of p-level amplitudes. And I can use that to basically fix what the entire integrand has to be. And the cuts that you have to use to calculate the integrand for this contribution are all
Is the point that you need to go to higher loops because there are some contributions that.
Yeah, you need.
Namely, you would say that you consider only tree level because you're looking at the leading order in H bar. Then you say because of the large mass, there is some series or a special kind of.
Yes, yeah.
Higher order diagrams that you need to sum.
Yes. Sorry. Yeah, good point. When I'm taking the classical limit, I'm taking the limit q goes to q bar, k goes to h bar divided by k. The additional limit you need to take, so you actually have contributions at a higher loop to leading order in h bar, is you need to assume square root of g. Our g goes as g divided by h bar.
This type of expansions, then it's, usually there's an infinite number of loop diagrams, right?
Yes, yeah, but you find out that each loop contributes at 1 over b. So you can pull out a factor of the impact parameter. So when you're computing like the tree level piece is like leading order in 1 over b. And then as you go to higher and higher order, you're doing an expansion in your quantum numbers. I am doing an expansion in the quantum number that I'm taking to be large, which is b. And the higher loop contributions correspond to doing like higher loop contributions of 1 over b.
Oh, I see. So it would be correct if you're only interested in the largest term.
Yes, yeah.
Okay. So,
yeah.
So there's a really transformation between the expansion parameter and b, and so
Yes, yeah.
you don't need to summon it in a diagram.
No. The statement that I'm going to make here is, so you have to do this expansion, which I described before, and then this expansion in G, which does what you say, and that it gets the higher loop contributions to also contribute at leading order. You can show that it fixes G to have this H bar contribution. In addition to this, you also need to assume that the loop momentum also scales with H bar. To get the leading order in H bar contribution. So when I do this computation, I take my integrands, I perform this rescaling on all terms of my integrands, and then I take a series expansion H bar and I take the leading order term.
The black hole masses scale.
The black hole masses, for the tree level, it's M1 squared. At loop level, you get a contribution that's M1 cubed, M2 squared, and then another one where it's flipped. You can also think of, yeah.
I think Offer was asking probably whether the masses go like 1 over H bar.
You can, I am in this scaling, I am not scaling the masses in any way, but you can just show that from dimensional analysis that there are a limited number of dimensions in the problem, that the scaling that I'm doing is equivalent to saying at any given order, I am taking a large mass limit. I don't know the precise, if I do that limit, I don't know how I need to scale G, which is why I didn't do it. And I can't figure it, like, someone can do it, I'm just not gonna do it off the top of my head, but you could just figure out how you could, instead of doing the scaling over Q and K and stuff, you could just do a scaling in M instead, and it's equivalent because there are a limited number of mass scales.
It's just the exchanges. I mean, that's the kind of familiar bound state, and something, blah, blah, ladder diagrams, giving us classical physics.
Yeah.
But, and now this is some radiation. Where does radiation reaction come in?
Radiation reaction, so this is the Donald O'Connell paper. I actually think, okay, so I'm gonna say what Donald O'Connell says roughly. Donald O'Connell roughly says that the radiation reaction comes from like this T dagger OT term and some other terms you can do a rearrangement. It comes from like the imaginary part. So he does his entire analysis in E&M, and he does a matching of self force with E&M with radiation reaction. I have not verified it for gravity, and there's weird stuff that happens for gravity, which I'm going to get to at the end of the talk. So I'm actually not, I'm not going to make any comment for gravity. I'm just going to say that radiation reaction E&M, you can relate to like T dagger OT terms, roughly, like the imaginary part of this matrix element. For gravity, I think it is more complicated, and that is something that I'm currently like trying to work on.
Just a very naive question. I mean, that there was the old, in all the radiation reaction problems going back to Abraham Lorentz, Dirac, all those people, the third order equations, all those funny things that we couldn't figure out. Is that, I mean, quantum field theory doesn't have any of those problems, so in principle, they should be solved, but there's no H bars in the solution, right? I mean,
I'm taking the leading order in H bar. Yeah. Yeah, there's only, I'm not including any higher order H bar contributions. Is that what you're getting at?
well, what I want to know is the resolution of those problems seen classically or not?
Yes, I think so.
So sorry, if we just choose a unit where H bar equals 1, can we think about this expansion as for the expansion in terms of a GM over the impact parameter?
Yes, that's a good,
Right?
that's like H is dimensional, like H, I wrote H bar here, but the H is just the statement of what scales I'm taking to be small. It's not like, I'm trying to, like, quantum physics emerges in large quantum numbers. And these are the quantum, this is the quantum number I'm taking to be large. And I'm saying because I'm taking it, the scale is 1 over H bar, where H bar is the thing I'm taking to be small. Wait, to get back, wait, I just want to say, so yeah, I think those things are resolved in his paper for E&M. He has a very detailed calculation that shows that he does this computation in E&M where he computes the radiation reaction, and then he does the same computation using like novel like self-force techniques and shows that they like match onto each other. That is my understanding. Maybe I didn't read through the paper carefully enough. I did not see the same computation for gravity.
So how does the H bar scaling factor in for when you're taking the small small momentum transfer limit? Does that?
So this is a statement here, the thing in ...
Yeah.
that you have to assume that you're only taking the leading order H bar contribution there.
But does that not influence, like, you're taking things that are beyond leading order in the loop diagram? So when you start.
So you have to compute everything that enters the ... and you will find that all the super classical stuff cancels. Like in intermediate steps here, you find super classical terms, but in the final step, you find that they all cancel. So basically you only needed to ever compute the classical term to begin with.
So you only need to keep the leading piece, or you think?
Yes, the thing that enters in ... which is not the amplitude, I only need to take the leading piece. And there is a leading piece at all loops. But the amplitude does not have a leading piece at all loops. But this is not an amplitude. You're taking combinations of different things.
You said that the one loop is H bar suppressed, or is it?
No, H bar, one loop is not H bar suppressed. You can show that there's a leading contribution of one loop in H bar that contributes the same like order as the tree level amplitude. And the loop comes out as being 1 over B suppressed. So 1 over the impact parameter. When you do this when you're doing a quantum expansion, or sorry, classical expansion, I am doing an expansion and the thing I am taking to be large or small. And that here is B, it's the impact parameter. So when I'm doing loops, I'm computing corrections to my system in 1 over the impact parameter. The leading order contribution, just tree level, is the statement of the things are like infinitely far away and like really not interacting that much at all. But as they get closer to each other, as you include corrections that they're actually not infinitely far apart, there are like systematic corrections in 1 over B.
This G, there is AG, and the one which is saying this part, that's perfect.
What?
So GN over B, that's the same as the risk.
Well,
Yeah.
yes, GN over, so it's
GN over B.
GN over B, this is what you're.
Yes, yeah,
And that's an expansion GN over B.
yes.
Yeah, on top of that, there will be some extra time correction.
So I'm a bit confused. If you boost the black hole, so the expansion is really m over the radius, the size of the black hole over the impact parameter.
Yes, yeah.
If you boost the black hole, then there is another scale in the problem. Like you can have, a small mass with a large energy, basically 2 shock waves that collide.
Sorry, I don't.
2 gravitational shock
Yeah,
waves.
the velocity, I guess. It's asking about the velocity.
Okay, I'm not assuming any scaling about the velocity. The functions that you get at each loop order are very non-trivial functions of the velocity. This is not a post-Newtonian expansion. I am not making any assumptions that I'm reducing to Newtonian physics. This is including full GR, but M divided by B expansion. There is a different expansion, which is post-Newtonian, which is actually what the upcoming paper by Demore is doing, but that is like a different calculation. Are there any other questions on the H bar expansion?
So these loop level objects are amplitudes that you're comparing.
Yes, so now you use because the intermediate terms are amplitudes. So I compute like amplitudes and then I take the integrand and I rescale all my stuff according to this H bar. And then I just take the leading, it's not the leading term for the amplitude, but I get to like the classical term, the term that's classical scaling. And I can discard everything else because they all cancel anyway between these terms. I will note that okay, I'm going to go back to how you compute it, and then I'm going to say how the integral simplified. So currently the computation that I'm describing is at the level of the quantum integrand. I have not taken any classical limit here. So you were saying you are basically constructing the integrand by saying if I take like these propagators to be on shell that I've written, and you sew together tree point amplitudes, that the integrand has to reduce to these things when I take these particular propagators that I've shown to be on shell. And you can use this technique. You have to do a lot of cuts to do this at 5 points. So these cuts plus this cut, and then you have to take all possible permutations of these as well. And then this will give you the full quantum amplitude. And then what happens here is you take the H bar expansion, and something like I get to the simplification that I mentioned at the beginning of the talk. You find that a lot of scales drop out in the leading H bar expansion. So in the H bar expansion, like these integrals, like M enters, if you compute this full integral, M enters non-trivial. A final amplitude is a non-trivial function of M. But once you do the classical expansion and you do this expansion HR, you find out that you can actually pull M out. So the entire integrand is actually just proportional to M. And there is a sense in which the entire these amplitudes, like the number of scales that they depend on, reduces a lot. Okay, so that's what we did. We computed each of the objects here by using generalized unitarity. We took the H bar expansion. You found that the integral simplified. They're 1 loop integrals. 1 loop integrals have been solved. You then just do the Queen Mary people did differential equations. Sebastian Hobby did differential equations. We just computed it using standard techniques. Because all of the integrals are of the form like a rational function plus 1 over maybe a square root or a rational function as log. You get nothing there's no more complicated function than log. The things that enter in here might be algebraic, but they're just logs. So they're not that hard to evaluate. Okay, so now in the last, I had 3 minutes extra. So in the last 6 minutes, I will get to the actual physics of why this is interesting, because everything that I've described so far is mostly algorithmic. So there's 2 real physics things that are interesting. The first one is that there is an IR divergence. So you can show that when you compute the amplitude, we do it in dim reg. So we assume that we're working in 4 minus 2 epsilon dimension, where epsilon is negative. And you find an IR divergence of the form. So y is a function of the energy. You can, this is where I'm like y, like the final integrals are a function of y, and y is the energy, and it's purely covariant, as you can see. This is an IR divergence. IR divergences are bad. M tree. However, something that is been known for a while to amplitudologists or people is that IR divergences exponentiate. So you notice that this IR divergence is proportional to M tree. And you can show that if you actually did computed the full expression, you could absorb this 1 over epsilon. So I'll write this function over here times something that's finite. This thing is just a function of y's, and it exponentiates, and you can systematically compute what this finite piece is, which is what we do. This IR divergence, there's an I here. You might naively think, okay, it's an IR divergence, amplitudes of IR divergences. That means it's not well defined, throw it away. All of gravity is dumb. But what actually just ends up happening is you just absorb it into the definition of omega. So note this is proportional to omega and a function of y. You just take that exponentiation and you just shift t by an infinite amount. And then you can actually do a GR calculation that was in Sebastian Hoppe's paper, where you systematically compute what this IR divergence is. If you look at my paper, you will see an incorrect calculation, which is what we are correcting, which is we don't correctly include this term in the IR divergence, but we have added in the correction term and we know that it is there. And roughly what happens is that this term corresponds to the Shapiro time delay. So it takes an infinite amount of time for the graviton to escape the well. And then this term, which is more complicated, comes from the fact that the graviton is interacting with the massive incoming states. So they derive this by considering a Schwarzschild approximation and just saying how is this scattering event shifted? There's a delay when the actual event happens compared to what you would imagine.
So is the one just the Weinberg part?
Yes, yeah, the Weinberg just Weinberg part, yeah. Okay, so this is physical effect number 1. That's the first 3 minutes. I have another 3 minutes. Now we get to physical effect number 2, which is a much more interesting one. Which is, some of you may have heard of the memory effect.
If you're computing the inclusive observables, should it actually free of IR divergence?
So it's not free of IR divergence. You get an IR divergence, but it exponentiates and you can absorb it into the time. You can say that the time at which you measure the event is divergently shifted into the future, but you can't it basically just means that you can't measure the time since the event happened. The event happens, there's a fall off in 1 over the spatial, but then you don't actually know when the event happened in the past because there is an IR divergence there that you shifted by.
Is it proportional to the sum of the masses of the black holes? Or?
No, it's the P1 and P2 are both, it's M1 minus, it's M1 times M2. But yes, it's proportional to M1 times M2. Since if you P1 and P2 both scale as M1 and M2 respectively. There's also a square root of G there.
So the delay relative to if you have only one black hole?
No, okay, here I can draw out the picture. There's a very nice picture. This is one just taken from their paper. Basically, so if I do a scattering event and fixed impact parameter, there will be a delay in when the event actually happens due to the fact that the black holes are like interacting with each other. And you can derive this from a probe approximation. Well, another way that you can derive it, which again they also had, is that going back to your Wilson line comment, you can show that if I replace a black hole with Wilson lines, that doesn't get me the correct answer, but the result gets me something that has the same IR divergence. So you can also just do a computation with Wilson lines and show that the expression that you get has the same IR divergence exponentiation that I've written down, which is what they do in their appendix. So these are two different arguments for it. The first one is like, this is two contributions to the shift in time, which is when the scattering event happens, and then versus it takes an infinite amount of time for the gravity, like gravity doesn't fall off quickly enough. And then there is a second, more formal argument, which is just if I replace my black holes with Wilson lines, I should get the same result. And then you can also just do a direct formal calculation there. And both of them produce the same result.
The fact that the one becomes two in this shockwave limit, I goes to infinity, it must have a simple.
Yes, it does. I have not thought about the shockwave limit. We're
It's factor of two in the fraction of light relative to Newtonian.
I have not thought about the large Y limit. Usually you think of, yeah, sure. Yes. I think, yes, okay. I think I agree with your statement. Usually we're interested in the Y to 1 limit because that's the low velocity regime. Sorry, I want to say the last thing, which is the memory. So there's statements that you can, if you have a LIGO, like a measurement, there is a memory effect. So the metric doesn't go back to its original form if you go from t negative infinity to infinity. There is arguments from Strominger that people pointed out that you can relate this to the soft limit. And this is basically just the statement that when I'm doing this Fourier transform, when I'm taking the Fourier transform in 1 over omega, that's just the sine function. Basically, the 1 over omega divergence is what controls the memory effect of the expression. Colloquially, there is an expression, a term for the memory. There is a general argument in the physics literature that you can just derive the memory effect from the Weinberg soft factor. So you have the Weinberg soft factor, which tells you that these expressions have a universal soft limit. And this gives you a universal expression for what the memory should be. We seem to be finding that is not actually, maybe not quite correct. And the reason for that is that the Weinberg soft limit applies to the amplitude, but it actually does not apply to this inclusive amplitude. So when you compute these terms, when you compute these three terms, the first two terms, and subtract all super classical, they just cancel among each other. The first two terms give you the desirable Weinberg soft factor that you would expect, even at one loop. We can show that it holds at all, but that's what we say in our paper. The additional point that was pointed out in the Sebastian Hobby paper is that there's one contribution that we ignored in the T diver OT contribution. When you include that contribution, we seem to find that actually does not have an interpretation in terms of the Weinberg soft factor. So this means that the soft limit at subleading order in 1 over B, like the 1 over B correction to the soft limit, does not seem, we do not seem to find currently that it actually takes like that it takes the form that is currently stated. This is a lot of the calculations that we are currently comparing against basically do amplitudes calculations, so they're computing exclusive observables. But there seems to be a fundamental difference when you're computing the soft limit between the exclusive observable and inclusive observable.
Is that just the fact that the Y part is not the Weinberg soft factor?
It's part, sorry. You would think, but we're having trouble actually relating the two. Part of the issue here is that the soft factor that we get out does not have a nice expression. It's not just like the traditional soft factor times like an additional like function of Y or something like that. It actually it's not human readable, which is the reason why I'm not writing it. Okay, it is human readable if you like type on the tech, it's like 2 lines, but I don't. It's not like if I write it down, none of you will remember anything other than the first term. But this is something that we are very interested in because it's a fundamental difference between exclusive amplitude and an inclusive amplitude, and would be something that's like fundamentally been missed, if it's true. We will note that that's part of why we're so interested in this upcoming paper by Demore, that we are currently trying to compare with him about whether he actually finds this contribution or not in his PN expansion. But that is something that is like still actively ongoing. That is, yeah.
So the iron divergence purely comes from the soft sector. There's no.
It's a sorry, this IR divergence comes from intermediate photons being soft. Weinberg, the memory effect comes from the external graviton, not photon, external graviton being soft. These are two different things. They are related to each other, but it's not immediate how to derive one from the other. And if you can, like what I would really want is a GR like calculation of what this memory effect is, because there's like a very nice GR interpretation of the memory effect for amplitudes. It's asymptotic symmetries or whatever, but it's not clear how I would actually compute the memory effect we are computing from GR, like where that is coming from. So if you have questions on that, I will not be able to answer that because that's something we're still active.
Sorry, I'm not asking something else.
Yeah.
I was asking if there's some intermediate collinear loop momentum, is that still giving you some divergence, or it's?
I don't think so, or at least we haven't, like, we only went to one loop and we didn't see any. At higher loop it is possible. Weird stuff, like I don't think anyone has seen anything at 4 point, to my knowledge. Weird stuff happens at 5 point. It's possible that there's some interesting physics there in the collinear limit, but that is not something I've explored. I would guess no, but just based on 4 point, but we've been wrong before using that intuition. I think that's it.
Okay, we've already had a number of questions, but is there anything else? All right, if not, then let's thank Aidan once again.